Today's activity is going to be on static friction. The problem is going to be essentially to find the coefficient of static friction. But you know, the problem always should be phrased in the form of a what? A question, right? So it's not going to be not per se to find the coefficient of static friction, but rather the problem might be something like, what is the coefficient of static friction? But be careful here, okay? You want to be specific. What is the coefficient of static friction? Well, there's a million different coefficients of static friction. What is the coefficient of static friction between this material and that material? Whatever two materials it is that you're using, you got to specify that in your problem, okay? What is the coefficient of friction between static friction between this and between that? What materials are we using? What's this called? It's a measuring scale, right? We call it a triple beam balance scale. It's used to measure mass. You're going to need to measure the mass of whatever it is that you're pulling. And I'll explain that in just a moment here, okay? But you're going to pull something, essentially. You need to know what the mass of that something is. Okay, this is what you're going to pull. This is a mass set. It's great the way these are set up. These mass sets come in these blocks of wood. This wood, or this block of wood, of course, has a wooden surface on the bottom. You're going to pull that wooden surface along your desk, or along the floor, or along something. Okay? And that wooden surface is going to have a certain coefficient of friction as it's pulled along that desk or that floor or something. The beauty of this setup that we have here is that we don't have to come up with another material to put these masses on. Okay, the case that carries the masses is our material. So we're just going to pull it with the masses in it. Now we have to change the mass. So what you're going to want to do here is take masses out. Take different combinations of masses out. Or put masses in. Doesn't really matter. You just need to change the mass of this block, of this mass set. Okay, does that make sense? You can see right here that there's a whole bunch of masses stuck on the back of that. Okay, that's fine. Add your keys to it. Add more masses to it. Add whatever you want to it. Add quarters to it. It doesn't matter, as long as you're changing the mass of this mass set. This is what we call a force sensor. It's an electronic force sensor, which is going to, through the AirLink apparatus, is going to beam the data for force to your iPhones. This is the old version, essentially, of the AirLink. Okay, we're using something that looks a little bit different, but you guys have seen it enough times now that you know exactly what that's going to look like. Okay, how's this going to work? Well, you're going to pull on this block. Here, let's go back to the picture for a second. You're going to pull on this block. Initially, this block isn't going to move. You're going to pull on it harder and harder and harder until it moves. The maximum force that the force sensor read would be the maximum force of static friction. Does that make sense? You should see, okay, when you use your iPhone, okay, to collect this data, you should see a graph for each trial that might look something like this. Force versus time. The graph would increase in force, increasing force, increasing force, and then it should go down. And then maybe over like this. The shape may not be as perfect as this. That's okay. But the bottom line is there should be a peak there. That peak corresponds to the force that you pulled with when it began to move. That's the maximum force of static friction. Okay, does that make sense? You need to record that. You need to record that maximum force of static friction. And then you're going to do another trial. What are you going to change in the next trial? The mass. Well, it's the mass directly, but the point of changing the mass is to change not so much the mass, but the normal force, right? So we're going to change the normal force. We're going to see how the force of friction responds to that normal force. And then what are we going to keep the same? Well, everything else. There's one thing that's really, really important that you recognize as control variables. Okay, you've got to get that. There's a lot of things that should be controlled, a lot of things that should stay the same, but there's something that's critical. If you change this, then this experiment is useless. Okay, there's no point in even doing it if you change this. So basically, it's everything else, but you've got to recognize what that one thing is that's so important that you don't change. Okay, it's the single most important thing that stays the same. So manipulated variable is what you changed. Okay, we talked about that just a second ago. The responding variable is what changes because of that. We talked about that. And then the control variables are all those things that stay the same. Okay, we want you to list 2 or 3 good ones. Okay, including that one that you can't change under any circumstances in the middle of an experiment, otherwise messes everything up. What's the procedure look like? Well, essentially, all you're going to do is take this force meter, attach it to the string that's on the end of this wooden block, and pull it. Pull it slowly. Okay, don't give it a quick jerk. Okay, give it a little bit of a pull until it starts moving. Okay? But there's a couple of settings that you got to watch out for here as well. On your iPhone, you should have an opportunity to measure either a force pull positive or a force push positive. You want to make the setting force pull positive. Okay, if it gives you that option, make the force pull positive. Essentially what that does is tells the apparatus when to make it positive and when to make it negative. We don't want to be pulling it and have the force measurer or the force meter measure it as negative values. When we pull it, we want the force meter to measure it as positive values. If you forget to change that setting, it's not the end of the world. It's just that you'll get all negative values for your data. Does that make sense? And your graph won't look like this. Your graph will look more like this. And your maximum force would be this as a negative answer. Does that make sense? You just take the absolute value for that. So it's not the end of the world, but if you catch that, then make the change so that all your values are going to be positive values. Measure the mass of the wooden block, including any masses of the wooden block, in the wooden block. Here's what I would suggest. So you don't have to keep going back and measuring masses 10 different times for 10 different trials. Measure the mass of the wooden block itself with nothing else on it. And then add masses to it. But these masses have the mass recorded on it. So if the mass of the wooden block is 200 grams and you add 100 to it, the new mass is 300 grams, right? So if you keep doing it that way, you don't have to keep remeasuring it for every single trial. Okay, measure the mass of the box or the block without the masses in it, and then just add the masses to it, add them up. Then you're going to pull the force sensor. Okay, press start, not on the Explorer. We're using your iPhones for this, right? Press start on the iPhones, and then you're going to pull it parallel to the ground. This is important. This is important. Why do I need to pull it parallel to the ground? Why, if the block of wood is right here and I pull it up like this, why does that mess things up? If I pull it up at an angle like that, the normal force is a lot harder to calculate because the normal force isn't mg anymore. I'm helping the normal force. Right? Gravity pulls down, the upward force has to balance it, but the normal force isn't the only upward force now. Right? There's a y component to how hard I'm pulling up. So you want to pull it parallel to the ground like this so that the normal force will be exactly equal to gravity. Since you're recording the normal force, m times g, it's really important that you have it parallel so that normal force is m times g and not some kind of crazy component of the force that you're pulling with. Right? So pull it parallel to the ground until it begins to move. Press stop. Okay, press stop on the force sensor on your iPhone. Record the maximum value of static friction. Record that value. If you can get it right off of reading the graph on your iPhone, don't even bother emailing it to yourself. If you can get the maximum force of static friction just by reading it off of the graph on your iPhone, just write it down. Can you save yourself that hassle of emailing it to you and all your partners? Just write it down. It says download the data to your computer. We're not downloading the data to the computer, right? You're emailing the data to yourself unless you can read it right off of the graph on your iPhone. Then, this is a bit of an outdated procedure, actually. Sorry, guys. Then you want to determine the maximum value. Then you're going to want to plot a graph. And the graph that you're going to plot is maximum static friction versus the normal force. So the graph, your data table is going to look like this. Okay, you've got your mass, and then you get your max force of static friction. You've got your analysis, which is still the mass and the max force of static friction, but also your calculation of the normal force, which is going to be m times g. And then under analysis, you're going to plot that graph of max force of static friction versus the normal force. It should look something like this. What do you think you're going to do in order now to calculate the coefficient of static friction, which, remember, was the whole point of this activity? What are you going to do with this graph? Take a guess. Yeah, take the slope of it. Okay, the slope of this graph will be the coefficient of static friction. Once we have that value, you're ready for a conclusion. The conclusion is, what is the coefficient of static friction? 0.75. This is known because the slope of a friction force versus normal force graph was 0.75, or whatever the case may be. Sources of error, don't forget your suggestions for improvement with your sources of error. All right, any questions on that? Yep.